Let us start by describing some important discrete distributions. A discrete distribution is linked to a discrete variable, and so we can list all of the outcomes. So we can make a list with all the possible outcomes, and we can then also assign probabilities to each of the outcomes. A lot of the discrete distributions are a result from gambling theory. People were gambling, they observed certain patterns in the data, and they tried to describe this in a mathematical way, giving rise to a distribution of a random variable. So they observed the pattern, they saw the possible outcomes, and then they attributed probabilities to the different possible outcomes. The most basic discrete distribution is the Bernoulli distribution, which was described by the French mathematician Bernoulli. In this distribution, we have a random variable which can have only two outcomes. One outcome is coded as failure, often indicated by 0. The other outcome is success, which we indicate by 1. Please note that failure and success are relative terms. So if, for example, you have a study where you look at the gender of someone, you could say that man is success in this study and a woman is failure. This does not mean that man is better or worse than woman. It just means that you are interested or you are coding the fact that someone is a man as being a success, just to make the difference between the two classes and to make the difference between the probabilities for success and failure. And then the distribution will just describe how likely it is to observe 0 or 1. Let's look at two very simple examples. For the first one, we flip a coin and we call a head, the outcome heads, is a success. So if it is heads, you get paid a certain amount. What are then the probabilities? If it is a fair coin, you expect that the probability for heads and the probability for tails is the same. So you would have a probability of 50% for failure and 50% for success, or you have a probability 50% for an outcome 0 and 50% for an outcome 1. Another option might be rolling a die. You roll a die, a 6-sided die, and if you roll a 1, then you win. In all other cases, you lose. So you have again two outcomes, success and failure, but the probabilities are now different. There is one side in which case you win, so 1 out of 6 sides gives you a gain, and so success has a probability of 1 over 6. On the other hand, there are 5 sides in which you lose, so you have 5 divided by 6 probability of losing, of having a failure. So the probabilities are actually just the proportions of zeros and ones that we would observe if we keep repeating the experiment. So if we do the experiment an infinite number of times. Why an infinite number of times? Just think of the example of the coin flip. We flip a coin and we have a theoretical probability of 50% to find heads, a theoretical probability of 50% to find tails. However, when you flip a coin in reality, you will see that you will not get an exact 50-50 distribution. You will not get that half of the coin flips is heads and half of the coin flips is tails. There is always some variation, some randomness in it, which will become clear from the following experiment. So suppose we flip a coin 20 times and we get the following results. As before, we will say that heads is success, tails is failure. We can then calculate the probability for success after each of the steps. So after 1 flip, after 2 flips, after 3 flips, and so on. If we plot this, we get the following progression. We know that the theoretical probability would be 50% for heads. Let us indicate this theoretical probability with a red dotted line. The probability for heads after 1 flip is 1. After 2 flips, it becomes 1/2, so 50%. We are on the line. Then we have another head. It becomes 2 over 3, 2 over 4, 2 over 5, and so on and so on. What we see is that the progression goes up and down irregularly, depending on heads and tails that we obtained in our experiment. Sometimes we arrive exactly at the theoretical probability of 0.5. Sometimes we are above this probability, sometimes we are below. And we are crossing up and down, just depending on the observations that we made. However, we can observe that the farther we go, the less pronounced the deviations from the red line will be. So the more observations we take, the better our estimate will remain close to the red line. So we will get a better approximation of the true theoretical probability. This is also why we say that the probability would be the probability as if we had an infinite sample, so as if we would take the limit for the sample size going to infinity. Graphically, we can describe a discrete distribution through a probability mass function, or in short, a PMF. Such a probability mass function just gives you the different options that the distribution has, and on top of that option you see a bar which is equal to the size of the probability corresponding to that outcome or to that class. If you think back to the previous chapter, this basically corresponds to a bar plot, a relative bar plot, but now for an infinite sample. That's also why there is a line on top of the class and not a bar. So we have an infinite sample, but we make basically a bar plot for that infinite sample. We can also make such a probability mass function for the two examples that we used. So on the one hand, if we have a coin flip, we have two classes 0 and 1, and for each of the classes the probability is 1/2. If we think back of rolling a die where 1 is success and everything else is a failure, we have a class for success 1 which has a probability 1/6. We have a class for failure 0 which has a probability of 5/6. Then a final remark on probabilities. A set of probabilities has to fulfill two conditions. First of all, every probability will be between 0 and 1. So any single probability can never be smaller than 0 or larger than 1. And on the other hand, the sum of the probabilities for all the possible outcomes is always equal to 1. Next to the probability mass function, there is a second function which is associated with a distribution, and this is the cumulative distribution function. Cumulative distribution function, or CDF, is nothing else as the probability that my random variable is smaller or equal than a certain value. So in the case of a discrete distribution, we look at the different outcomes which are possible, and then we look at the probabilities that are associated with those outcomes. In the case of a Bernoulli distribution, there are only two possible outcomes. And then we look at the probabilities. So we have two possible outcomes, 0 and 1. And let's call the probability to have a 0 pi 0. Let's call the probability to have a 1 pi 1. What we then do is we draw these probabilities, or we draw the sum of these probabilities in a graph. For the Bernoulli distribution, we know that the sum of pi 0 and pi 1 is equal to 1. Then we have to look at what are the options. So what is the option to have a value which is strictly smaller than 0? That option is 0. There is no probability to have this value because the only value you can have is 0 or 1. If you arrive at 0, it means you have a probability of pi 0. So you arrive at 0, which is not included from the left, and then you jump to pi 0 because that is the probability that x is equal to 0. And then the next jump in your function will happen at the value 1. Why? Because at the value 1, so x equal to 1, you have a new probability pi 1. And so you have to add this to the previous one and you jump up with the value pi 1. So between 0 and 1, with 1 not included, you have a probability of pi 0. But once you arrive at 1, you have to look at the probability that x is smaller or equal than 1. X is smaller or equal than 1, in this case is x equal to 0 plus x equal to 1. So you have a probability pi 0 plus a probability pi 1, and you jump to a value of 1. So a probability value of 1. What you note is that you always start at 0 at the left for a cumulative distribution function, and you will always end at 1 because you have added all the different probabilities together, and the sum of all different probabilities is always equal to 1. So this slide summarizes the Bernoulli distribution. We have two probabilities, a probability to observe 0 or to observe a failure, which we call pi 0, and a probability to observe 1 pi 1. Pi 0 is just the proportions of zeros in an infinitely large sample, so it is how often you would see the outcome 0 if you repeat the experiment an infinite number of times. Pi 1 is the proportion of ones in such an infinite large sample. Since you only have two options, pi 0 plus pi 1 will always be equal to 1, because any experiment has to be either 0 or 1, and so any of the experiments has to be in one of the categories, either in the 0 category or in the 1 category. Also, you only need 1. If you know pi 0, you know pi 1 as well, or vice versa. If pi 1 is given, you know pi 0. And then in general, we say that a discrete distribution for a random variable describes the different values that the random variable can take on, but also the probabilities assigned to each of those values. So a discrete distribution is not only the values or not only the probabilities, but always the combination of all values with their corresponding probabilities. The second distribution is the binomial distribution. So consider n independent observations, and each of the observations has two possible outcomes, success or failure. So basically what we do is we repeat n times a Bernoulli experiment. So we have n identical Bernoulli experiments. All of the experiments have the same probability for success, the same probability for failure. The random variable x that we are then interested in is the number of successes among the n observations. So we have n repeated experiments and we look at how often do we have a success. So how many ones are there in all the Bernoulli experiments. And so actually what we do is we count the number of successes in all the experiments. The values, the possible outcomes for x are therefore 0 up to n. We can have either 0 successes, 1 success, or every experiment is a success, and then we have an outcome of n. We have n successes over n observations. A binomial distribution will be associated with two parameters. A parameter n, which indicates how many observations, how many independent observations you will have. So how often do I repeat the experiment? And a parameter p, which gives you the probability for success. So you always give the probability for success, not the probability for failure. And then a binomial distribution is indicated as b, so the b for binomial, with parameters n and p. And then trivially, the Bernoulli distribution will be a special case of the binomial distribution with just one single experiment. So a Bernoulli distribution is a binomial distribution where n is equal to 1. So once again, a binomial distribution is a repetition of n times a Bernoulli experiment, but it is very important that those experiments are held independently of each other. So the outcome of one of the experiments cannot influence the other experiments. So each of the Bernoulli experiments has to be done separately from each other experiment. They cannot influence each other at all. Let's consider the following example. Suppose that the probability for male or female hyena cubs is the same. And then assume that x is the number of female cubs in a nest of 5 cubs. What do we know? We know that the probabilities are the same, so the probability for success is 1/2. And we also know that we are looking at the number of female cubs. So in this case, success is a female, and then what you want to do is you want to count the number of successes over 5 cubs. 5 cubs means that you can have either 0 to 5 females, and so you will have to look at the probabilities for each of those outcomes. So you will have to calculate the probability that there are no female cubs up to the probability that there are 5 female cubs. How to calculate these probabilities we will see in chapter 6, but for now they are given in the table. What you can observe is that, again, as it should be, the sum of all these probabilities is equal to 1. And if we draw the probability mass function, we see that it looks like the graph below. From the table as well as from the graph, we can see that the binomial distribution is a symmetrical distribution. So the left side and the right side of the distribution are the same. Consider rolling a die. So if you have a die, there are 6 sides, and normally each of the sides has the same probability. So the probability for an outcome 1 is 1/6, 2 is 1/6, and so on, up to the outcome 6 is 1/6. Every side has the same probability, 1/6. What we observe is also here that each of the probabilities is between 0 and 1, and the sum of all those probabilities is equal to 1, which is also illustrated by the probability mass function. In this specific example, the probabilities for all the outcomes is the same. However, you can also imagine examples where this is not the case. So you have probabilities for each of the outcomes, but they do not necessarily have to be all the same. Even though we have multiple possible outcomes, it will not be a binomial distribution. A binomial distribution looks at the number of successes among a number of observations. Here, we do not look at numbers of successes, we just look at the outcomes themselves. So each outcome, each possible value of the die is a success in itself. It is an outcome in itself. And so we assign a probability to each of the outcomes, but nowhere do we count a number of successes. A multinomial distribution is then a generalization of a binomial distribution. Again, we repeat an experiment, but this time the experiment has more than 2 possible outcomes. So we repeat it independently, but instead of only success and failure, we have more than 2 outcomes. For example, you could roll the die, let's say 4 times, and then you see what comes out, and you want to know the probability. So for example, what is the probability to roll 1 times a 2, 2 times a 4, and 1 times a 6? So we suppose that there are n observations with k possible outcomes. So we have n independent experiments. Each of the experiments has k possible outcomes. And we denote xi, the number of observations in class I. So in xi, you just see how often you have that outcome. Pi I is then the probability for an observation of that class. And then the multinomial distribution describes all the probabilities such that you have a probability for x1 is x1. So you have x1 observations in class 1, you have x2 observations in class 2, and you have xk observations in class k. So for the example given above, you would get the probability that x1 is 0. So there are no observations in class 1, there are no observations with outcome 1. And that x2 is equal to 1, so we have 1 times a 2. x3 is equal to 0, x4 is equal to 2, x5 is equal to 0, and x6 is equal to 1. And then the final discrete one that we will discuss is the Poisson distribution. This distribution could be used, for example, to map the population of seals in Alaska. So you would take aerial photos and then you just count the number of seals over a certain area. So a Poisson distribution in general describes the number of events in a given time frame or in a given area. So you count, but always within a certain limitation. So within a certain time frame or within a certain area. The possible outcomes for this distribution are 0 to infinity. So theoretically, you can have any number, any natural number as an outcome. And then for each of those numbers, you will have to assign a probability. So the probability x equal to k is just the probability in our example of seeing exactly k seals in that area. For a Poisson distribution, the mean is always equal to the variance, and the Poisson distribution will be denoted by p, and we'll have only one parameter, a single parameter lambda, which is at the same time the mean and the variance. The probability mass function is given on the right side of the slide, so it looks relatively symmetric, but it's no guarantee. Not every Poisson distribution is symmetric, it will depend on the parameter. In red is indicated the mean, so it is in this case 15, but you also see that the tail on the right side is still a little heavier than the tail on the left side. And this skewness, this will become more explicit once your parameter changes. Another option might be to think of counting the number of cars at a certain crossroad during one day. So you look at a crossroad, you count the cars and you have a limited time frame. So one day long you count how many cars pass that crossroad. There is a drawback to the Poisson distribution, namely that it has only one parameter for both the mean and the variance at the same time. In reality, if you look at biological counting processes, the variance is often larger than the mean, and so we need an alternative parameterization, so we need an alternative distribution to look at this process. In this case, what you will be using is a negative binomial distribution. So a negative binomial distribution does exactly the same as a Poisson distribution, but it has a parameter for mean and a separate parameter for the variance. So the negative binomial distribution is also called the over-dispersed Poisson distribution. And below you also see that it is more explicitly skewed than the Poisson distribution.